everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. We are doing a series of lectures on the course Engineering Physics for first year BTech students. And we have started the module 5. And yesterday we have already discussed about simple harmonic oscillators. And today we are going to discuss about damped harmonic oscillators. And those who have not seen the video on simple harmonic oscillators, I request you to go through the video first before going through damped harmonic oscillators, because it is a continuation of simple harmonic oscillators where we have discussed all the basics of a simple harmonic motion. So now let us go into the subject, that is damped harmonic oscillator. So let us see how we are going to discuss this topic. First, we are going to derive the expression for damped mechanical oscillator. And then we will try to understand the conditions for damping in mechanical oscillators. And also we will try to understand this concept with the help of a few applications that we see in our day-to-day life. And then we are going to derive an expression for damped electrical oscillator. This is a simple mechanical oscillator. It is a damped mechanical oscillator. And we are also going to derive damped electrical oscillator. So for both, and also the conditions for damping in electrical oscillator, we are just going to discuss the conditions. So now coming to damped harmonic oscillators, as I told you, whatever we have discussed yesterday, we have discussed in detail about a simple mechanical harmonic oscillator. Means if you take a harmonic oscillator and just disturb its position and leave, we expect that the oscillator keeps on vibrating, and we are not considering the forces that are acting on them. And all physical systems involve considerations such as air resistance, friction, and intermolecular forces where the energy in the system is lost in the form of heat, sound, etc. Means if we are taking an oscillator which is oscillating, definitely there will be some resistance due to the air that opposes the motion of this oscillator. And we have neglected this. We have not talked about it when we were dealing with simple harmonic motion. But that is an idealistic case, means only in an ideal situation we say that there are no forces acting on the oscillator. But in practical, if you see, there are a number of forces that act on this oscillator. So accounting for damping is very important in a realistic oscillatory system. So we also have to consider what are the damping forces that are acting on the system on an oscillator. Then what happens when there is damping? The oscillation with which the amplitude decreases gradually. With time, they are called as damped oscillations. Now, when we are talking about an oscillator, you disturb it from the free position. It keeps on oscillating if there is no resistance to it or no damping forces. But when there is a force, a damping force or a resisting force acting on this oscillator, the amplitude will gradually die down. So for example, if you see a simple pendulum which is suspended from a rigid support, if I take it to one end and leave, this will keep on oscillating like this. There will be a number of oscillations like this. This we are considering when there are no damping forces or no resisting forces acting upon the system. But even if there is some air resistance on the motion of this oscillator, the amplitude decreases gradually. So if you can understand what is amplitude, the maximum displacement from the mean position. We have seen all the definitions in the previous lecture. So the maximum displacement it can have in either direction, we are calling it as the amplitude. So here what happens, because of damping, the amplitude gradually decreases and eventually the system comes to rest. So how we are going to define oscillators or damped harmonic oscillators? They are vibrating systems for which the amplitude of vibration decreases over time. So in a damped harmonic oscillator, that is the vibrating system, the amplitude of the vibration decreases gradually with time. That is how we are going to define a damped harmonic oscillator. Now let us see one example. We'll consider the same example of the spring that we have discussed in simple harmonic oscillator, and we'll try to understand. So in that, what we have seen is we have taken a spring. To one end of the spring, a block of mass m is attached, and this end is fixed to a rigid support. So when we are displacing it through a distance x, there will be a force acting in the opposite direction, which brings it back to its original position. That is what we have seen. So we have considered a block of mass m, and it is connected to a spring whose spring constant is k. And in the ideal situation, what happened if we push the block a little and release, it keeps on oscillating. Means I have just displaced it through a distance x and left it. So it keeps on oscillating about the mean position. If you consider this is the mean position, it keeps on oscillating. And the angular frequency of the oscillation is given by omega is equal to under root k by m. So omega here represents the angular frequency. This is angular frequency. And k represents the spring constant. And m is the mass. So the angular frequency, the frequency with which it is oscillating, the angular frequency is given by under root k by m. So it depends upon the spring constant as well as the mass of the object. Now we are going to look at damped harmonic oscillator. Means in the same oscillator, if there is damping, then what happens? So what we are going to see is, in practice, an external force, if the object is suspended freely in air, so the damping force will be due to the air. So there will be a damping force that is exerted on the motion of the block, and the mechanical energy of the spring system will decrease. You see here, this is the rigid support. We are suspending a bob with the help of a spring. This is the spring. We just pull it down and release it. Now when you are moving it through a distance x, there is a force, restoring force, that tries to bring it back to its normal position, which we call as a restoring force, given by minus kx. This we have seen. Now what we are talking about is a damping force. The resistance due to the air that obstructs the motion of this object, we are calling it as the damping force. And this damping force also acts in the direction opposite. And because of this, what happens? There is some energy loss that occurs in the system. And the energy that is lost may appear in the form of heat in the surrounding medium. So the first thing what we need to understand here is, whenever we are talking about an oscillator, even if it is suspended in air, there is a damping force that acts on the oscillator, and this damping force acts in the direction opposite to the motion of the object. So while we try to write the expression, we also have to consider the damping force. Now this damping force depends upon the velocity with which the mass is oscillating, and also on the nature of the surrounding medium. So it depends upon the velocity, means we are moving it through a distance x in time t, so you can calculate the velocity. And also it depends upon the mass, because when we are talking about spring constant k, it is in turn dependent on the spring constant and the mass. And it also depends upon the nature of the surrounding medium. What is the nature of the medium in which this system is oscillating? So for example, we'll take a block which will be immersed in a liquid now. We'll take some liquid. You see here, this is the liquid in a beaker. The same system we have considered. This is a rigid support. This is the spring. And this is the block. When we just displace the block, disturb and leave it, it keeps on oscillating. Before we have seen what happens when it is moving in air. Now we are considering if it is kept immersed in a liquid, then what happens? The magnitude of damping will be more. So there will be more damping because there will be more resistive forces acting upon the object and the dissipation of energy is much faster. And if this liquid is replaced with some other liquid whose viscosity is high, means it depends upon the nature of the liquid we have seen, the nature of the surrounding medium. Now we are taking oil. Suppose we are taking some oil, say cooking oil, and you immerse this object in it. Definitely there is some damping force which is greater than that in air. Now if this liquid or this oil is replaced with some other oil whose viscosity is high, maybe we'll replace it with castor oil whose viscosity is very high. Okay, then what happens? The damping will be much more greater. So this shows that it depends upon the nature of the medium in which it is oscillating. Now let us try to derive the expression for damped harmonic oscillator. So the damping force is proportional to the velocity. So this is the first point. What we need to understand is the damping force depends upon the velocity and it is directly proportional. Means if the velocity with which the object is moving is more, the damping force is also more. And it acts in the direction opposite to the velocity. So the first point is it is directly proportional to the velocity, and the second point is it is opposite to the direction of velocity, means opposite to the direction in which it is moving. So now we'll write the expression for damping force. So damping force FD, F usually denotes the force. We are putting a suffix D to denote that it is a damping force. So always the damping force is denoted by F suffix D. Okay. So the damping force is proportional to velocity. So I write FD is proportional to velocity. And it is opposite in direction. So I will add the sign also. So I'll write it as minus V because it is opposite in direction. Now I will remove the proportionality sign and put a constant, and that constant is gamma. Minus is already there. So how we are going to write the expression for FD is minus gamma V. FD is equal to minus gamma V. This is equal to minus gamma. What is V here? V is the velocity. And we know velocity is nothing but rate of change of displacement, which is denoted by dx by dt. So we are going to write for V here dx by dt. So let this be equation 1. So FD is given by minus gamma dx by dt. And this constant gamma depends on the properties of the medium, that is viscosity. For example, here we have taken oil and with different viscosities we have seen. So gamma depends upon the medium, that is like the viscosity or the shape and size of the object. Now we have taken a block. So we may take a block which is spherical in shape. We may take a rectangular block or a block of bigger size. So when this changes, the shape or the size of the object changes, or the nature of the liquid, that is the viscosity of the liquid varies, gamma varies. So gamma depends upon the viscosity or the nature of the object. Now what we are going to do is we are going to write the net force. What is the net force that is acting on the system. We have already discussed that there is a force that tries to bring it back to the normal position or the equilibrium position, where that force is proportional to the displacement, and we have written it as minus kx, where minus k denotes that it is opposite in direction and k is the constant. So here now we are having two forces. One is the force, the restoring force that brings it back to its equilibrium position. This is also opposite in direction to the displacement. And now this is one. And now we also have the damping force, which is also acting in a direction opposite to the velocity. So we are now going to write the net force. So the net force F is equal to minus kx minus gamma v. So we understand all the terms. F here denotes the net force. So the net force F is equal to minus kx. K is the spring constant and gamma is the constant which depends upon the properties of the liquid or the media. Now let us write the expression for F according to Newton's second law of motion. F is equal to ma. Force is equal to mass into acceleration. We have now seen the expression F is equal to minus kx minus gamma v. So for F, we are going to substitute ma because F is equal to ma according to Newton's second law of motion. This is a universal law for every motion. So we are writing ma is equal to minus kx minus gamma v. Let us take it as equation 2. Now we will substitute for a. What is acceleration a? How do we define acceleration? Acceleration a is the rate of change of velocity. A is equal to dv by dt. It is the v represents the velocity. So the rate of change of velocity. With respect to time, we are talking about is acceleration. And we also know that velocity is the rate of change of displacement dx by dt. So we can substitute for v here. We'll get a is equal to d by dt of dx by dt. That gives us d square x by dt squared. So the acceleration is given by d square x by dt square. So in place of a, we are going to write d square x by dt square. So m into d square x by dt square plus gamma into dx by dt. What is v here? V is nothing but dx by dt, rate of change of displacement. So we have put for v dx by dt plus kx. See here what we have done. We are bringing all the terms onto one side. I can write one more expression here. ma is plus kx because on the right hand side it is minus kx. I transpose it and bring it onto the left side. We get plus kx plus gamma v is equal to 0. ma plus kx plus gamma v is equal to 0. So here for a we have substituted d square x by dt square, and for v we have substituted dx by dt, and kx term remains the same. So this is equation 3. Now this equation describes the motion of the block under the influence of damping force, which is proportional to velocity. So this equation, what it describes, it is also including the damping forces that are acting on the system. One is the restoring force and also the other one is the damping force. Now let us write this equation again. What we have now is d square x by dt square m we had plus gamma dx by dt plus kx is equal to 0. This is what we had in equation 3. Now what we are going to do is divide throughout with m. So when you divide throughout with m, what we have? D square x by dt square plus gamma by m into dx by dt plus k by m into x is equal to 0. So that is what we are seeing here. So dividing equation 3 by m. So this m goes, and in the denominator you have m and m in both the terms. So d square x by dt square plus gamma by m into dx by dt plus k by m into x is equal to 0. So now what we are going to do here is, this is gamma. Gamma is a constant. It depends upon the nature of the liquid and the shape and size of the block we have seen. And the mass of the block is also a constant for a given system. So instead of having two constants, we are going to substitute for gamma by m. So let gamma by m be equal to 2b. This is gamma. Let gamma by m is equal to 2b. We are going to substitute because instead of having two constants, we are writing one constant, 2 into b. And we know that k by m is omega square, the square of the angular frequency. So for k by m, we are substituting omega square. So for k by m, if you substitute omega square, and for gamma by m, if you substitute 2b, what we are going to get? D square x by dt square plus 2b into dx by dt plus omega square x is equal to 0. So this is the expression for a damped harmonic oscillator. And the general solution for this is given by x is equal to a1 exponential minus b plus under root b square minus omega square plus a2 exponential minus b minus under root b square minus omega square into t, where a1 and a2 are constants. We are not going in depth about this solution. This is just to understand how the solution of this second order differential equation is going to be. And that gives us the displacement of the object which is in motion. Now let us understand what are the types of damping we have here, depending upon the values of b and omega. We have taken b as a constant, gamma by m we have taken as 2b, and omega is under root k by m. So depending upon these two values, we are having different cases in damping. The first one is underdamped. Underdamped means what? The system oscillates with the amplitude and gradually decreases to 0. So this is what we have seen. What happens here? The system will oscillate. It will oscillate with decreasing amplitude. The amplitude goes on decreasing and then it comes to rest. So this is what we have seen in underdamping. Then overdamping. What is overdamping? The system returns to equilibrium without oscillating. It will not oscillate at all. Means I disturb the object from here, it will come back and it will come to rest. That's all. That is overdamping. And the third one is critical damping. Here, the system returns to equilibrium as quickly as possible without oscillating. Means when we disturb it here, it comes very quickly to the equilibrium position. So in both these cases, in overdamping as well as critically damping, there is no oscillating. The system comes to the equilibrium position without oscillating. Only in the case of underdamping, it is going to oscillate, the amplitude decreases gradually and then it comes to rest. Now, if you see different cases of damping, every type of damping has its own application. In some cases, we may need underdamping. In some cases, we may need overdamping. And in certain areas, we need critical damping. So, we are going to understand that with the help of examples. So, let us see the graph for these three cases. So, the first one here is overdamping. Overdamping means it will come to rest without oscillating. So, the green line, this one means the green line shows that the system is not oscillating. It will just come to rest. Then what is the difference between overdamping and critical damping? We have seen that in critical damping, the system comes to rest within the least possible time. Means very quickly it comes to rest. So you see here the red line 2 denotes critical damping. So you see here it comes to rest very fast. So you see the amount, the exponential decrease in displacement with respect to time. So this comes to rest here itself, whereas this comes to rest in overdamping. It takes a longer time, but in critical damping, it comes to rest faster. And the third one is underdamping. So 3 is underdamping. Underdamping means what? The system oscillates. In these two cases, the system is not oscillating. You see, the curve is just an exponential, it is dying off. But here, in case of underdamping, the system oscillates. It oscillates, but it oscillates with decreasing amplitude. The amplitude goes on decreasing gradually, and gradually it comes to rest. So this is the difference. With the help of the graph, you can understand all the 3 different cases. Now let us see each case and the conditions for underdamping. See, because wherever you need underdamping, what are the conditions that it has to satisfy so that the system is underdamped? So in underdamped, what we need to understand is it oscillates and the amplitude decreases gradually, and then the system comes to rest. So what is the condition for underdamping? B square should be less than omega square. So what is the value we have taken? Gamma by m is taken as 2b. So I can write b is equal to gamma upon 2m. So b square should be less than omega square. So what is b square here? Gamma square upon 4m square should be less than omega square is k by m. So if this condition is satisfied, then what happens? There will be underdamping and the system will come to rest gradually. So for a system that has small amount of damping, the period and frequency are nearly the same, but the amplitude decreases. What you need to understand here in underdamping, we are talking about the amplitude goes on decreasing gradually. The amplitude is decreasing, but the period means the time period, the time it takes for one complete oscillation, and frequency means the number of oscillations it makes per second remains the same. Only thing is the amplitude goes on decreasing. This is in case of small amount of damping. Now, this occurs because the non-conservative damping force removes energy from the system, and it is usually in the form of heat. We have seen, we call it as thermal energy. So whatever heat that is lost into the surroundings, that is how the damping forces are happening. Now, if you gradually increase the amount of damping, means in small cases, in small amount of damping, the amplitude goes on decreasing, but the frequency and the time period remains the same. But if damping increases, if there is an increase in the amount of damping, then what happens? The period and frequency begin to get affected because the damping opposes and hence slows the back and forth motion. So as the amount of damping increases, the time period and the frequency also changes. This we will see in case of mass that is immersed in a fluid of low viscosity like thin oil or even just air. So air also offers some resistance. Because of that also there may be a damping force. So what we are seeing here is whenever the damping increases, the period and the time period and the frequency are also getting affected. Now the second case is critically damped. What is the condition for critically damped? B square should be equal to omega square. If in that particular system, if B square is equal to omega square, then the system returns to equilibrium as quickly as possible without oscillating. Now you want a system where you don't want any kind of oscillations. Once the system is disturbed, it has to come back to its equilibrium position very quickly. Then we need critical damping. So for critical damping, what is the care that we need to take is we have to see that B square is equal to omega square. If you can set the values of omega square, that is K by M, and B square, which is gamma square by 4M square, if you make them equal, then what happens? There will be critical damping, means the system will return to its equilibrium position as quickly as possible without oscillating. So how we are going to define this critical damping? If you are asked to define what is critical damping, it is defined as the condition in which the damping of an oscillator results in the oscillator returning as quickly as possible to its equilibrium position. So in this oscillator, it returns to its equilibrium position as quickly as possible. So that is the key word here in critical damping. If you see the graph here where we are plotting for distance versus time, what is happening here is it comes to rest quickly, very quickly. Now, where are the areas where we need critical damping? Critical damping is often desired when the system returns to equilibrium rapidly and remains at equilibrium. So where do we need this type of critical damping? For example, we take when you stand on a weighing machine, you want to check your weight and you stand on the weighing machine. So definitely there is a needle. If it is not an analog, if it's not a digital one, if it's an analog one, then the needle moves. The needle moves, it shows your weight. Then what happens? The needle, if you are on the machine, it has to come to the equilibrium position or it has to show the reading immediately. It cannot keep on oscillating. So what happens if it is oscillating? It would be quite inconvenient. You are very anxious to see your weight and the needle does not come to rest. So what happens? So it is not desired. So what we try to do here is we set the conditions for the needle, for the movement of the needle such that it is critically damped. Means it has to come back to the new equilibrium position, means whatever weight it has to show, that will be the new equilibrium position. So it has to come to that position, okay, and it has to come to the position very fast, as quickly as possible. And these damping forces can vary in character, means depending upon the type of system we are taking, they may vary. Now the third case is overdamped. We have seen underdamped and we have seen critically damped and now overdamped. So in what is the condition for overdamped? If B square is equal to omega square, then there is overdamping. So in overdamping also, there is no oscillation. The system comes to rest or to equilibrium without oscillating, but more slowly. It will come very slowly when compared to critical damping, because in critical damping, it is coming to rest as quickly as possible. But here, it takes time and it depends upon how overdamped it is. So the amount of time it takes to come to rest depends upon how overdamped it is. And as with critical damping, it may also overshoot, but it will reach the equilibrium position over a longer period of time. So with overdamping, what we need to understand is the condition. If B square is greater than omega square, there will be overdamping. And in overdamping, it reaches the equilibrium over a longer period of time. So the displacement plot for overdamping would appear as shown in the figure. So we have seen that in overdamping also, depending upon how much damp, if it is lightly overdamped or highly overdamped, how it is going to be. So now if it is slightly overdamped, so what is the graph we have here? Okay. And if it is highly overdamped, this is the green line we have seen. If it is highly overdamped, in all the three cases, it is not oscillating, it comes to rest. Okay. but at different time intervals. So this is almost coming to rest here. And if you see the violet line, this is coming to rest here, and this may take a longer time. So in case of overdamping, more the time it takes to come to rest or to come to equilibrium. So here we are seeing at slightly different overdamping. Now, we'll try to understand the concept what we have discussed with the help of the example. An example which we see in our day-to-day life. Okay. So what we are going to consider is a door that uses a spring to close the door after opening. So in most of the cases you see in the figure here, this is what we are talking about. This is a door closure. So we are using a spring mechanism to close the door. After opening, the door has to close automatically. So for that we are using a spring. And when we are using this for closing the door, there may be different types of damping depending upon the strength of damping. Whatever damping we are applying here, depending upon that the door closes. So now in case the door is undamped means there is no damping at all. Then what happens once you open the door? The door keeps on oscillating and it will not come to rest because there is no damping at all. We have discussed the ideal case where there are no resistive forces at all. So what happens? The door will continue its oscillations without coming to rest with a particular frequency. So it will swing back and forth with a particular frequency. So is it designed? No. Now the second case. If it is underdamped, what happens? It will swing back and forth with decreasing amplitude and then it will come to rest. So when you open the door and come inside, the door has to close automatically, but it does not close immediately, but it will oscillate with decreasing amplitude and then slowly it comes to equilibrium position. So is it required for it to oscillate? No. Now the third case, if it is critically damped, then it will return to the closed position as quickly as possible without oscillating. So when you open the door and come inside, you don't want the door to oscillate, and also it has to close in a smooth manner in the least possible time. So for that what we do is critical damping. So in the door closure, what type of damping we need is critical damping, so that the door will close automatically without oscillating and it will happen in the least possible time. So that is what we are going to see in the application here for a door. So we are also discussing, understanding all the different cases. Undamped, it is not required because it will keep on oscillating. Underdamping, it will oscillate and then it will come to rest, not required. But critical damping, in critical damping, it will come to rest in the least possible time. Now if you see example 2. In example 2, we are talking about the recoil of a gun. What is this recoil mechanism? You all must be knowing about the recoiling of a gun. So when a bullet is fired from the gun will recoil back. You must have studied it under Newton's third law of motion. So for every action, there is always an equal and opposite reaction. So when the bullet is moving in the forward direction, the gun recoils in the backward direction. But if you compare, the mass of the bullet is small, so the velocity is more. But here, the mass of the gun is more, so the velocity will be less. So it will not move with a greater velocity, but still it will recoil back. Now, in this case also, Most guns are critically damped so that they will return to their original position after recoil in the least possible time. So when a bullet is fired from a gun, if the gun is oscillating because of the recoil velocity, it is very uncomfortable for the person who is handling the gun. So what we need here is critical damping. As soon as the bullet is fired, the gun recoils back, but it has to come back to the equilibrium position without oscillating in the least possible time. So what we need here is critical damping. Now let us see example 3. This is a best example for overdamping. So in overdamping, what happens? It cannot come to rest immediately or in the least possible time, but it will come slowly. So when we want to damp out oscillations, such as in the case of the suspension of a car, and we want the system to return to equilibrium as quickly as possible. But with less than critical damping, the system will return to equilibrium faster, but it will overshoot across one or more times. That is the problem. What we are trying to understand, you imagine that you are traveling in a car, okay, and then it goes on a speed breaker and very fast. It is moving with a higher velocity without, if the driver doesn't slow down, we understand, we all experience what happens. So then what happens? You may get displaced. You may get a jerk upward. But once the jerk, if the spring system is not perfect, then what happens? You may overshoot or you may get hurt. Then what happens after that? You will have to come back to your equilibrium position slowly. Otherwise, what happens if it is critically damped? You will just come down with a thud. No, and then again you will get hurt. So what is required here is overdamping, because in overdamping, the system comes to rest very slowly. Okay, and the same example with a coiled spring mattress. So you know the mattress on which we sleep. So if it is a coiled spring mattress, when you jump onto the mattress, what happens? You will push the mattress inside. But if it tries to come back to the original position in the least possible time, then what happens? You will get a jerk again, or you may jump out of the bed. So what is required here is, after that, it has to come to the equilibrium position very slowly or gradually and without oscillating. So in such case, what we need is overdamping. So what we see here is, wherever humans are involved, we are trying to see that there is no critical damping. It cannot come back to its equilibrium position very fast. It has to come gradually without oscillating. So what we go for is overdamping. We go for the condition of overdamping. Now the example 5. We have seen the example where we need critical damping, where we need overdamping. So do you think that damping is very much required? No. There may be some cases where we don't need any damping, which we call it as underdamping. Why damping is not required, we'll try to understand. For example, the vibrations of the strings in a guitar. You know guitar, it has strings which we pluck and then we hear the music. For that matter, any stringed musical instrument you take, a guitar or violin or veena, all these are stringed musical instruments. So you will pluck the wires and they keep vibrating. So when they are vibrating, they produce a musical sound. Now suppose you imagine when you pluck the string, without oscillating, the string will come back very quickly to its mean position or the equilibrium position. Then you will not hear any music, it will be only a noise. So what is required here is underdamping. You need that the wires will vibrate, and then they will come to rest gradually. That is what we are calling as underdamping. So what we are seeing here, any stringed musical instrument, it should be underdamped. Otherwise, what happens? The sound will simply be a loud noise. And the same thing with the bell. You see the ringing of the bell, maybe in the temple or in a school or a college, we see the bell ringing, the old conventional bells. When you ring, what happens? It will vibrate, 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 and gradually the sound will die off. Means the vibrations will come to rest gradually. Otherwise, it will become very difficult for us to hear the noise. And one more example is the simple pendulum. So we have already discussed this many times. When you are talking about a simple pendulum, when you disturb it from its equilibrium position, it will vibrate and then slowly it comes to rest. Now the degrees of damping, we may call them as degrees of damping also. We are just quickly revising what we have seen. In underdamping, the body will oscillate before coming to rest, that is at the equilibrium position. And in critical damping, the body will come to rest in the shortest possible time without oscillating. And in overdamping, the body will take longer time to come to rest without oscillating. And all three are required. So in some cases, we need underdamping, like in the case of stringed instruments. And in some cases, we need critical damping, like we have seen in a door or the recoil of a gun. And in some cases, we want overdamping, where it has to come to rest gradually, like the case of a mattress or in a car, the recoil mechanism in the car. We need overdamping. Now we are going to discuss about damped electrical oscillator. See, what we have seen till now is a mechanical system. So now when you are dealing with electrical systems, now there may be oscillations. Now what are these oscillations here? So when we are talking about these electric and the magnetic fields that are moving in a medium, then what happens? Then also there is some kind of damping. So what is the damping and what is the equation related to it, we are going to understand. So what is the system we are considering here is a LCR circuit, an electrical circuit which consists of an inductance L. This is the inductance L, and a resistance R and a capacitance C. This is the capacitance. So that is what we call as LCR circuit. So according to Kirchhoff's law, the total voltage due to the inductance VL, resistance R and C should be equal to 0. VL plus VR plus VC should be equal to 0. What is VL? The voltage that occurs across the inductor. This is VL. So how do we measure VL? VL is equal to L into di by dt, the rate at which the current flows through the inductance. So VL is given by L into di by dt, and the voltage across the resistance is given by VR, that is IR, which we know is the Ohm's law. VR is equal to IR, and VC is the voltage across the capacitance, that is given by Q upon C. And Kirchhoff's law tells us that in a closed circuit, in a closed loop, the sum of the voltages is equal to 0. So VL plus VR plus VC is equal to 0. Now let us substitute for VL, VR and VC. What is VL? L into di by dt. VR is IR and VC is Q by C. So the sum is equal to 0. Now let us write the equation for a damped electrical oscillator. So what is I here? I is the current, which is nothing but the rate of flow of charge gives the current. I is equal to dq by dt. So let us substitute for I here, dq by dt. So d by dt of dq by dt gives us d square q by dt square. So L into d square q by dt square plus R into I. What is I? dq by dt. So we have R into dq by dt plus q by c is equal to 0. Now we will divide throughout with L so that we will get a differential equation of second order. So when we divide throughout with L, what we get? D square q by dt square plus R by L into dq by dt plus Q by LC is equal to 0. So this is the second order differential equation. So what we are getting here is a equation for damped electrical oscillator. And the solution of it gives us the charge Q e power minus bt A1 e power alpha t plus A2 e power minus alpha t. What is alpha? Alpha is beta square minus omega square power half, and omega square is equal to 1 upon LC, because we are considering the LCR circuit, and beta is equal to R upon 2L. Now what are the conditions for damping here? If beta square is less than omega square, we have light damping. So what is beta square less than omega square? Omega is under root 1 by LC. So omega square is 1 by LC and beta square is R square by 4L. So if R square by 4L is less than 1 by LC, there is light damping. And if beta square is greater than omega square, means R square by 4L greater than 1 by LC, there will be heavy damping. And when beta square is equal to omega square, then there is critical damping. So these are the three conditions for damping in electrical oscillators. For more information regarding this topic on electrical oscillators or damped harmonic oscillators, you can refer to books Engineering Physics by Harbola, Vijay Krishna and Madhumohan. That is by Cengage Publications, or you can also refer to Gaur and Gupta Engineering Physics. Thank you, and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.